Class. I am so excited. I'm ready to jump out of my skin, so I hope I can read this. This is a huge privilege for me as a scientist to be here with Dr. Cambell today. So Dr. Cambell, thank you so much for being here. Good morning, everyone. It is my privilege to introduce our speaker today, Dr. William C. Cambell. Dr. Cambell spent almost 33 years working in the area of parasitology for the Merck Institute for Therapeutic Research. After leaving Merck, Dr. Cambell spent the next 20 years working at a number of prestigious colleges and universities, including the University of Pennsylvania, New York Medical College, and Drew University. Dr. Cambell is currently an associate fellow for the Research Institute for Scientists Emeriti at Drew University. Dr. Cambell earned numerous awards and honors throughout his career, including membership to the National Academy of Sciences and honorary degrees and awards from college and universities all over the world. And in fact, told me this morning, I'm adding this, that he sat next to Kareem Abdul-Jabbar on Saturday. So those of you in the room can ask about that. Sorry. Dr. Cambell is here today to share some of his, thoughts on his life's work in parasitology, work that earned him and jointly Dr. Satoshi Amura the Nobel Prize in Physiology or Medicine in 2015. Dr. Cambell will be sharing a snapshot of the research that earned him this prestigious honor, as well as his thoughts on the experience of winning the Nobel Prize. Following our time together in chapel today, refreshments will be available in the Frick, and I encourage you to come and meet Dr. Cambell there in person. Please give a warm welcome to Dr. William C. Cambell.
Thank you, Dr. Karabetsos. It's great to be here at Brooks School. I think of myself as being something of a neighbor because I live just across the lake. I spend a lot of time on the lake. For a moment, I considered coming here this morning in my kayak, but I decided that arriving in my old kayaking shorts probably would bar me from entry. But I'm very glad to be here. I know some of you have already learned something about parasites, and there are few things better to study. Maybe there's nothing better to study than parasites. They are such wonderful creatures, and they have impact on our lives that we just don't even think about. We think maybe in terms of disease, but the cost of a chicken dinner depends on parasite control, and the softness of our sweater depends on parasite control, and the durability of our shoe leather. And so perhaps even our response to fear might be affected by parasites. So there are many, many different parasites that do many, many different things. But this morning I'm going to, is it morning? Yes, it is morning. I'm going to talk about one particular parasite and one particular disease. And when you reach a really, really old age, people start asking you about your past. They know you don't have a future. They ask you. So I get asked this all the time. So I feel it's sort of mandatory. I'm going to begin with a few biographical slides just to explain how I got very improbably here today. Again, it's part of this sentimentality of age. I tend now to always have a cover slide of my hometown in Ireland. And that is it. And this is also it. This is the street I grew up on. Those happen to be my father's cows and dogs and shop, that black thing, and so on. And this is where I first heard about parasitic worms. And some of you have been learning about parasites. You know that there are many different kinds. Most of them very small, protozoa, for example. Then there are organisms like bacteria and viruses that live a sort of parasitic life, but by convention are not lumped in with parasites. But I like something bigger. I like the worms. And I've been interested in worms ever since I was in high school. And I went to an agricultural agricultural show as a school outing, and heard about liver fluke, a parasitic worm of sheep and cattle, and about a particular drug, and I remember what drug it was, so I put it on the slide here. And that moment did not change my life. I did not decide to work on parasites, but looking back on it, I know that as soon as I heard about them, I thought they were fascinating, and I still do. And so just a couple of biographical things from that town and from a boarding school in the city. I went to Trinity College Dublin, where I met, not only met, but encountered Professor Desmond Smith, who changed my life. He was a parasitologist, and that really, really established and crystallized my interest in parasites. And from there, I crossed the sea, thanks to Professor Smith, to University of Wisconsin, where I did my graduate work. And from there, I went directly to the Merck Institute for Therapeutic Research, an arm of the Merck Pharmaceutical Company. And I worked there for 33 years and then went to spend 20 years at Drew University. And that's my life in a nutshell. So what I want to talk about is a roundworm parasite, that is a nematode, a roundworm, and a particular one, Onchocerca volvulus, which causes a very important disease which has got a lot of attention in recent years. And since it's caused by Onchocerca, the disease is onchocerciasis. But it is popularly known as river blindness. And as I will show in future slides, that is a sort of catchy name, but it's very, very misleading, because blindness is indeed the most serious consequence of the disease, but it is not the most common, and it is certainly not the only serious consequence of the disease. This gives you a very general idea of where it occurs throughout sub-Saharan Africa and into a little bit of the Middle East and in Central and South America. Now, within those white areas, there's not a uniform distribution. It varies a lot from place to place. So this is very much oversimplified, but it gives you some idea of where it occurs in the tropical regions of the world. And I'm not going to go into details about the life cycle, but it's necessary to know that it is transmitted by black flies. And those flies breed in rivers. The larvae are actually on stones and rocks under the water of fast-flowing streams. And those flies are associated with water, but it's only because the river blindness is associated with water only because the flies breed there. And here you see a fly, when it comes to a person and bites that person, it does not suck blood, it's not like a mosquito, but it dissolves a little bit of tissue around the bite site, makes a little soup that it will drink, and then in the process, it will deposit some larvae of Onchocerca. These are microscopic larvae of Onchocerca volvulus, and they will penetrate. Oops! Oh dear. Okay. Sorry. Oh dear. That's okay. There we are. I better maybe not try and use this pointer. So you can see where it has bitten the person. There are a few larvae have come in, and they settle down under the skin, and the host forms a capsule around them, and you have those worms then growing up to become adults. The female is very, very long, more than a foot and a half long. The male's been much, much shorter. And they mate there, and they produce offspring. They do not lay eggs. They give live birth to microscopic progeny called microfilariae, and those microfilariae migrate through skin. And here you see, I've just shown very crudely that they migrate all over the place. They do not head for the eye, but there are thousands and thousands and thousands of them being born every day, for every pair of worms. And so some of those, in migrating through the skin, will get into the eye and result in eye damage and blindness. And there is a mandatory developmental cycle in the fly, so it's not just a mechanical transmission. Now, here you see on the left an example of one of those capsules near the surface, so it is bulging. So you have this nodule, they're called nodules just in slang, on the skin. And so there's inside that nodule you see on the pelvic region, it's like a tennis ball full of spaghetti. It's usually not quite as big as a tennis ball, but it's a round capsule filled with these long, thin roundworms. And they are not tender, they're not painful, they're not tender to the touch. But they are the source of all the problems to follow. And you can see there a cross-section of skin with a larva in it, just give you some idea that they're not just superficial, they're right in the skin, migrating. And the picture on the right is an example of a kid who has been infected for maybe half a year. It takes a while for these worms to grow up, but when they start producing those microfilariae and they start migrating through the skin, you get a tremendous itching, which of course you don't see in a slide. And people don't think about it, they don't talk about it, the textbooks don't say much about it, but the itching alone is a huge, huge problem because the people in endemic areas get bitten zillions of times a day with these black flies if they're living near the rivers. And so just the sheer itching. But also you can see those striations there. That's not what the parasite does. That's what this kid has done in scratching himself because of the itch. But you can also see a rash there, a maculopapular rash. It has spots, but those little spots are little pimples. And so that's what happens early on. By early on, I mean at about half a year, when the larvae are migrating through the skin. But that happens for years and years because these adult worms live there for maybe 18 years. And so you have damage to the skin over many years. And on the upper left there you have this condition where the skin has been insulted so severely for so long that it has lost its elasticity and the skin has become wrinkled years before any wrinkle should appear. This is obviously a tremendous cosmetic problem. This is a condition known as presbydermia, and this will be meaningful to those of you who know about medicine or who know about religions, because especially Presbyterians, because this presbydermia simply means having an elder skin. So you have a young person with the skin of an elder. And so in the lower picture, you actually have a picture of a village elder, blind, and this is somebody I met in West Africa in northern Togo. And the people who were with me asked him if he would raise the hem of his garment, which he did, and revealed his legs, which has leopard skin, again a slang term for this condition, which is a condition of very, very abrupt, unusually abrupt depigmentation. So these things you can see are tremendous sociological problems. I mean, not only physical discomfort, but for young people, for teenagers, for example, they're more conscious of this than the fact that they're likely to go blind later in life, because this is what dominates their life when they're young. So this is a very serious dermatological disease. Some areas have such a high level of infection that the villages are abandoned. They are abandoned because they are close to the rivers, and therefore they're subject to bites of flies breeding in the rivers. And so this is a tragedy on many levels. It's obviously individual tragedy, but also a village tragedy because of the social disruption, which I'll mention later, and also a regional travesty because these villages become abandoned, such as this one. And this one obviously has been a very prosperous village to judge by its construction. So you have this tragedy of fertile land being abandoned as people go to unfertile lands. Okay, this is just to remind me to switch to another topic, to the disease itself. I like parasites so much, I paint them. These are tapeworms of sharks. But I want to turn now to something about the drug itself. One of the things that I've brought out in recent years as I've been asked to talk about this is that it was all so simple. The discovery of this drug, ivermectin, which is used for control of river blindness, was discovered in a mouse, not in an experimental group of 10 mice or 5 mice, but a mouse. And this was a mouse that was in a box in the lab at Merck Pharmaceutical Company, and it was being fed mouse food, and that food was temporarily adulterated by adding a liquid to it for 6 days, and then it got its regular food back, and then about a week later, this mouse, which had been infected experimentally with worm parasites, no longer had the worm parasites. They were gone. So, and I can tell you what day that was, the very day. Not that I was doing the experiment, but I mean, that was just a very clear indication of antiparasitic activity as observed in that single mouse. By single mouse, I don't mean that the mouse was unmarried. I mean that the mouse was just there by itself. Now, there were lots of other mice also getting different adulterations to their food and also having worms, but when they got their food temporarily adulterated, they did not lose their parasites. Now, when I say adulterated, I shouldn't really use that word because it's such a negative thing. But what I'm referring to is the fact that that diet had been supplemented, there, that's the word, it had been supplemented with a liquid. Actually, it was freeze-dried liquid, but it was a liquid in which bacteria had been allowed to multiply. In other words, it was a fermentation. So this is what bacteriologists call a fermentation broth. And this was added to the feed of the mouse. And the thing about it is that we didn't know what that bacterium was. We knew it was a bacterium. It had been sent to us by Professor Omura, whom was just mentioned because he shared the Nobel Prize. It was one of many bacteria cultures that he sent us. But we didn't know, and he didn't know, what it might be good for or what it was, what kind of bacterium. It was just one of those cultures you can find in the soil by the millions all the time. So we didn't know what it was, and we didn't know if it had anything in it that would be unusual, and if it did, we didn't know what that stuff would be. So this is a really crazy situation, which seems very unscientific at first, but it's really not unscientific. But we actually found this drug by feeding an unknown substance in unknown amount to a mouse, and we fed this mouse an unknown substance, an unknown amount that might not be there. In other words, we didn't know if there was anything there. So this, in fact, is a great way to discover a new drug. And I have been advocating for decades the empirical approach to drug discovery. And we may or may not have time to talk about that. But the thing I want to show now is that this was very, very simple. And mind you, thinking of the assay to do this was not simple. That was very innovative on the part of my colleagues because the other people weren't doing it. And bacteriologists were doing similar things for decades, because of the example of penicillin, to find new drugs as antibacterial agents. But parasitologists were not doing quite this thing, and they were not looking at microbes as culture. They were looking at synthetic chemicals as possible agents. Anyway, I don't want to get too distracted on that. But the thing is that sometimes simple science can really work. Not that the complicated science should be ignored, but that's a different subject. Okay, so here is the stuff. It looks a bit like a mold growing on an agar plate, but it's actually a filamentous bacterium. And our bacteriologists described it as a new species. It's a species of streptomycin. And, a species of streptomyces, the genus Streptomyces, but not the same one that produces streptomycin. And it produced a parasitic substance in that one mouse, and then we went on to test many mice, of course, and many, many other animals. But the thing about it was that it was not only active, but it was incredibly potent. This would have an effect in getting rid of worms when it was fed in the diet to mice at 0.0003%. Now, if you're not doing that sort of work, you think, well, that's sort of a meaningless figure. But believe me, that is absolutely unheard of. That was far more potent than even the most effective drug then known. Of the drugs that are out and used in the clinic and in the marketplace, no antiparasitic agent had anything like that potency, even when this was still in a crude form. So that naturally got our attention. Now, the stuff was ivermectin. That was what this bacterium was producing. And some of you undoubtedly are chemists or would be or going to be chemists. So our chemists always believe that nature, a bacterium, a microbe, can produce something that humans will never think of. But only a chemist can make it right, the chemists say. And they're right. I mean, they took this stuff and they made it even better. So what they started was with ivermectin, and they turned it into ivermectin. And those of you chemists will, of course, immediately have spotted the difference. But just in case you haven't spotted the difference, I will point out the difference lies in that upper right-hand section. The carbon 22-23 bond has been hydrogenated. It's represented on the top as a double bond, and here this has been hydrogenated, so this makes 22-23 dihydroivermectin, and that we gave the name ivermectin to it. Now, I'm going to talk about the disease of humans, river blindness, but before I do it, I just want to really, really emphasize that this drug was first and foremost a drug for use in animal health. And the thing to remember about it, as it is completely overlooked by those who are interested in the human disease, is that humans keep domestic animals for the sake of humans. They don't keep them for the fun of them. So controlling parasites in domestic animals and animals we have for food and fiber and companionship, those are important. So this drug became the dominant, and still is, and now there are various variants of it, the most important drug in animal health parasite control. My own personal at the bench thing was with dogs, because dogs suffer from dog heartworm disease, and we discovered in my lab that the activity was such that one could develop a once-a-month treatment to prevent heartworm in dogs, and that has become standard procedure for the prevention of heartworm in dogs. Okay, but it turned out, well, it seemed to me, on the basis of what we knew about many parasites in many animals, that it had a potential for use in river blindness. Because I was, as you had heard in the introduction, I taught helminthology, worm parasites, at New York Medical College, for example, and I was interested in it all my life. So it seemed to me that the connection between the different kinds of parasites pointed to the possibility that this would be useful in humans. And so this was tried and was very effective, and I had a chance to go when there were these early trials to see if it was safe enough to be used on a community basis, where you just simply go in, if there's a community that had a high incidence of infection, you just treat the community. And doing this, you would prevent disease developing. You would not get rid of the worms initially, but you would, by yearly treatment, you'd prevent the worms from developing, and you'd totally prevent disease. These are a couple of slides about these community trials. You see girls standing on the bathroom scale. On the right-hand side, this has since I was there, this is now replaced by a less expensive method, which is just a stick. And you see that stick being used on the lower right. It's not graduated in inches or centimeters or anything else. It's graduated in pills. And you get 1, 2, or 3, and you see this young woman, her height is such that it's a rough indication of her weight, and she qualifies to get 3 of these little pills. So this is much simpler than using a bathroom scale and much less expensive. The man in the top right is totally blind. He was at one of these gatherings that I was at in a schoolyard or under a tree where treatment was being administered. But for him, this would not help because his eyes are destroyed, and this drug cannot restore his sight. But it can completely prevent the development of the disease when administered to school children annually or semi-annually, and that has been done. But the question is, what do you do? This is the pictures show a very iconic sort of scene in Africa where you have blind adults being led by children. The upper right one, it occurs to me, and recently when I've seen that, it looks like this guy's on his cell phone, but he's not. He's holding on his shoulder the end of that long pole, which connects him to his parent or the adult who is blind. And on the lower left, you can see that a child is leading blind parents. So what do you do with a drug like that? Because these people cannot afford to buy a drug at any price. So the decision was made by the CEO of Merck that the drug would be donated to all who need it for river blindness for as long as it is needed. And that has been incredibly successful. Don't pay any attention to any details on this slide. It's because I have long since stopped updating it or paying attention to it, because the only thing is that it just shows a continued upward slant as more and more drug. These are numbers of treatments approved in millions. And it has continued, and it has become quite mind-boggling in the scope of it. Because, for example, this year I just learned on Saturday that Merck will be donating 900 million doses, and that the cumulative dosage that they've been given since it started has now just gone over 2 billion treatments. These are just other pictures of this iconic scene in Africa. These scenes should now be disappearing, but these kids, of course, should be in school. So this is just another example of what I mean by the tragedy on many levels, because apart from the adults being blind, you have children who are not in school because they're leading their parents around. And now those scenes are vanishing, and people are leaving the bad land and returning to the rivers, reclaiming huge, huge acreage of land, which is, of course, another aspect of it. And now they have switched the objective of controlling the disease to the objective of eliminating the disease. And it has been eliminated in 4 out of the 6 countries in South and Central America. And they're even trying to do the same thing in Africa, which is a much greater challenge. Okay, this picture shows me in 1992 at the United Nations talking to 3 very important people. The one next to me on the left is my wife, and I don't need to explain why she's a very important person. But the other 2 do need some explanation. Second to the right is Dr. Roy Vangelis, the person at Merck who took responsibility for making that decision. One reads and hears of other people proposing it and so on, but it's very easy to tell a big company to give something away, but the important thing is for somebody who has the authority to do it, to actually do it. And it turns out to be extremely difficult to give a drug away. And then on the far right is Jimmy Carter, former President Jimmy Carter. When he heard about giving it away, he first refused to believe it. He sent an emissary to Merck to ask, are you really going to keep doing that? And they said, well, we plan to do it forever. And they said, that's okay, forever's long enough. And so Jimmy Carter has done tremendous work in helping the distribution of the drug. There are more paintings of tapeworms, which we can pass over, but I must mean that I need to switch to some other topic, which is well, how are we doing for time? Are we all right? We got some time left? 10 minutes. Okay. So you heard at the beginning that there was this Nobel fuss in Stockholm, which in fact was an incredible thing. I would have expected that it was, a special day, but it's a special week. It's Nobel week in Stockholm. in December, and it is a most incredible fairy tale sort of thing. Flowers by the zillion sent from Italy every year, from the town where Alfred Nobel spent some of his final years. And but before you get, this has become a sort of tradition, is before you go to Stockholm to get the Nobel Prize, you get invited to the White House. So that is sort of a big stepping stone on the way to Stockholm, is to go to D.C. And this is my wife and I being received in the Oval Office by the president. Now, I mentioned that I had worked on dog heartworm as sort of my on-the-bench, hands-on part of this whole program. And to my amazement, after talking to the president for a little bit, he put his hand into his jacket pocket like this, and he pulled out something for me. And here it is. It's a stuffed animal in the shape of a dog heartworm. And it has a little, you might be able to see a little red embroidered heart on the top. It doesn't really look like a worm. Of course, it's much fatter than a worm would be, but it's the idea that counts. And it's actually labeled dog heartworm. And this was the only present he gave to those of us who were visiting. So needless to say, I still have that little stuffed animal. So then when we go to Stockholm, this is the setting for the Nobel ceremony with banks of people up on either side in the shadows there. Everybody's standing because the king is standing, handing stuff to me. My empty chair is over there on the left. That's a row of red seats. But there's another picture. This is a bit closer. It shows that this little circle with the N on it, and what you have to do, you're told what to do, of course. You stand in the little circle there, and the king gets up this. Let me try this, see if I can hit this little. There we are. This is the royal family here, the king and queen, Princess Victoria, the crown princess, and her husband, and then various other people. And a lot of flowers. I can tell you who the others are, but it's not worth the time. So you stand in this, and he comes up and greet you. And then I'd always heard as a kid about, in fairy tales, if you're in the presence of the king and you're leaving the room, you must walk backwards. But in this case, it's the king who walks backwards. He hands you the stuff, and then he walks backwards. And then I suppose it's so that you don't bump heads with the king. I don't know, because you bow to him then, and then you turn and you bow to these people here. These, in fact, are the committees who decide on the prize, which is a big operation, of course, lasting for years. And then, so you bow to the king and then these people, and then you bow to the audience. One of the things, it's a very, very dressed-up occasion. And my wife was the first to say, so it's all right for me to say, that what she worried about right from the beginning was what to wear. But she solved that problem beautifully, and so for her that was done. For me, there was no problem. We were told what to wear every day at every occasion. It was just amazing. And for me, there was no trouble deciding to wear this. The trouble was getting into it. It was a real nightmare. And the hotel is used to this, and they have a tailor on duty at the hotel all that afternoon to help rescue people like me. Even though I went to a boarding school where I learned to use collars with studs and things, but that shirt is so starched, it's like a plate of steel. I mean, it is really absolutely a nightmare. So here we are. Everybody gets to have a few minutes with the king and queen, and here we are with our few minutes just with them and a few security people in the background somewhere. And then incredible banquets. This happens to be, there's the Nobel banquet, which is just out of this world. And then this is the high table. And then the next day there's the royal banquet, where no pictures were taken. And so at this banquet, the king and queen were there, but you had to be careful not to say thank you if you had to make a speech, which fell to my lot to make a speech. But I had to be careful not to say thank you because he was a guest himself. But the next day at the royal banquet, then he was the host. So there are all these matters of protocol. Okay, so this finally is sort of the climax where he hands you these things, a little box with the medal in it, and the red thing underneath is a certificate with very fancy calligraphy, and that is it. And to me, I don't show those slides at the beginning and then end with this handshake through any sense of triumphalism, but sheer bewilderment. And that is the end. Thank you.